Hey everyone, let's pick it up at number 6. Okay, so once again we have power and root, and we're going to rewrite this in exponential form, so with a rational exponent. Our base, 9k, we're going to keep that in parentheses so we know the exponent is for all of that. So here's my power over root. And since the directions once again say do not simplify, we're not going to reduce the 2/4. All right, moving right along. Next, number 7, which expression is equivalent to the cube root of 8 to the 5th? So remember, this number is the root. This number is the power. So I'm looking for a root 3 and a power 5. On the first answer choice, do we have root 3 power 5? No, the exponent has the numbers in the reverse situation. If I was going to rewrite this, it would be 8 and then power over root. So this one does not match. On to part B, or answer choice B. I see the same problem. I need a root 3 and a power 5. So over here, my root is definitely not a 3. So this one is not correct. The last one, 2 to the 5th, that's our only choice. We're going to prove that it actually works. So I'm going to rewrite this a slightly different way. I'm going to do the cube root of 8 to the 5th, because that helps me. If I know the cube root of 8, I can say it's 2, and then 2 to the 5th, I can easily see that they match. If you check out the worked out solutions PowerPoint on PowerSchool, it has a different way of showing this answer. It doesn't come out 2 to the 5th, but you can still prove they're the same. So check that out if you want more information. All right, on to the next. To rationalize the denominator of that lovely fraction, by what expression would you multiply the numerator and denominator? So we want to know, what do we multiply by? So when we're doing rationalize the denominator, remember we need same root, like that. And then I look at each number or each variable. So I have 2 to the 1st. I need 3 altogether, so I'm going to do 2 to the 2nd. So that gives me 1, 2 in the first radical, and then 2 in the second. For the x's, I have two x's in the first radical, in that first cube root, so I'm going to add one more, or x to the 1st, so that when I multiply, they both end up with an exponent of 3, and that will get rid of our radical or our cube root. When I go to look for this answer down in the bottom, I don't find it. Instead, I find the simplified version. 2 squared is 4, and then I have x. That's answer choice C. On to the next. Which expression is equivalent to this? This one you would need to look back in, I believe it's section 11.2 from our notes, and look at, there were some rules. I believe this one is called the quotient property of roots. Essentially what it says is, as long as our roots are the same, we can do them separately, or we can squish them together like we see in answer choice B. And we're going to use that property both ways in just a few minutes. Number 10, which expression does not simplify to -6? Well, we're just going to go through and simplify each expression. So here I have square root of 9, which is 3. There was a negative in front, so I bring that over. Then times. The 5th root of 32 is 2, and since it has that negative with it inside, it comes out, comes out with it as well. Remember, odd roots will keep that same sign. So negative times a negative, I get +6. Remember, we're looking for the one that does not equal -6. So that actually is answer choice A. I'm going to do the rest just to make sure we understand the process here. So the next one, I'm going to end up squaring a negative, which means it's going to become +16. -4 times -4 is 16. Then I still have times the cube root of -27. All right, so then as I continue through, the 4th root of 16, if you're not sure, start breaking it down. But I happen to know that it is 2. And the cube root of 27 is 3. And again, since it's negative, I bring the negative, and that's how I get -6. So that one did match. The last one, again, simplifying, I have the cube root of 8, which is 2, and keep the negative. Then the square root of 9 is 3. Multiply those together, I get -6. So the only one that didn't work was A. Onwards. For 11 to 13, simplify the expression. Assume that all variables are positive. In simplified form, we need all our exponents to be positive, and we're going to rationalize any denominators that we need to. So this one, it's very, very tempting to do this. But keep in mind that doing this is wrong. The reason it's wrong is our roots are not the same. We have a square root and a fourth root, so we can't write it like that. Sorry, can't write it that way. What I can do then, I can't put them together. So what I do instead is I'm going to set this up to rewrite it into exponential notation. So I group everything in the root that's inside and then put it to the first power. So here's how it translates to exponential notation. I would say x cubed y to the power over root. And then this one is x squared y to the power over root. Once we have it like that, we can use our properties of exponents. So we're going to distribute the exponent, which gives me, sneak in a little 1 under that 3, and I get x to the 3 over 2, multiply there, and then y to the 1/2. In the denominator, similarly, we're going to distribute that exponent. So again, sneak a 1 under that 2, I get x to the 2/4 and y to the 1/4. Then, if you're sneaky here, we can see, if I kind of think of this as two separate fractions, I have like bases with x's, and I have like bases with y's. So when I divide like bases, I'm going to subtract those exponents. So for the x's, this is the x's, I'm doing 3 over 2 minus, rather than 2 over 4, if I reduce that, it'll help me out, I'll get a common denominator here. 2/4 is the same as 1/2. And then that makes it easier to subtract 2 over 2, which is 1. So in my answer here, I have x to the first, or just x. Remember, this was the exponent. All right, then for the y's, not an equal sign there. Let's fix that. For the y's, I'm going to do the same thing with those exponents. I'm going to subtract. So I have 1/2 minus 1/4. And whoopsie, I don't know where that came from. Okay. And when I go to subtract these, I do have a common denominator situation. I got to multiply that first one by 2 over 2. That gives me a new equation here of 2/4 minus 1/4, which equals 1/4. And again, remember, this is the exponent. This time it's for y, so y to the 1/4. And that's our answer. Any questions? Oh, wait, you can't ask me. Let's go on. Okay, number 13. This one I really like because if we look, this one, not 12, 13, has all matching roots. They're all the same. So with all the matching roots, we can do one big cube root and put everything under the same root or same radical. So when I simplify this one, lots of ways to do that. I'm just going to multiply it. So I get 24 over 3. Then I'm going to divide to simplify. I get 8, and the cube root of 8 is 2. Onwards. Number 14. This one's going to take a little bit of work here. All right, we have the period t of a pendulum as a function of its length L is given by the equation. Rewrite the expression, that's important, that's what we're doing. Rewrite the expression for the period as the product of a simplified coefficient term and a variable term using only positive exponents. We want positive exponents, and we are going to rationalize the denominator one more time. So those are the key parts there. There's a lot more there about coefficients and variables, and we're not going to focus too much on that. I'm really more interested in, can we rewrite the expression? So here goes. I start with t equals 2 pi square root of L over 32. I'm going to immediately split that square root so I can deal with my variable and my number separately, like that. Then I go back to the one I'm on, sorry. And then on this one, I can break down that 32. You can break it down any way you want, but since I have a square root here, I'm going to look for a perfect square. I happen to have 16 times 2 is 32. And I know the square root of 16 is 4. That's going to come in super handy in just a second. So here goes, t equals 2 pi